We're going to have a short recap of basic linear algebra. This should be mostly stuff that you will have seen in Math 200 here at Middlebury College or anywhere else where you had an introductory course to linear algebra. So today we're going to remind ourselves of vectors and vector spaces and their basic properties. We'll also look at the dot product and its algebraic and geometric formulae, and also how the dot product gives rise to notions of angle and magnitude or length. Finally, we will look at displacement vectors or geometric vectors, and these are really the vectors that you will have seen in high school, which are arrows and those quantities that have both magnitude and direction. Okay, so let's remind ourselves very quickly that vector spaces and linear maps are objects that we use to generalize the algebra of solution sets of systems of linear equations. The main and the essentially only example is the vector space Rn. This is the collection of all n by 1 column vectors. Remember that a column vector is a column having n entries, and each of those entries is going to be a real number. For example, here are some column vectors in R3 and in R4. Now don't worry if you're a bit put off by this set builder notation. We'll be using this over and over and over again, and very quickly you'll become accustomed to it. However, feel free to ask me during class or in office hours if you're having any trouble with these curly brackets or this weird looking E symbol that we've got right here. Remember that vectors can be added, so given any two vectors, and these have to both be vectors inside the same vector space, I can add them component-wise. Similarly, if I take a vector, I can scale it by some scalar, or a real number. What do is we take our scalar, lambda, and to scale our column vector, we just scale component-wise. Each of these operations satisfy a bunch of properties that you can find in page 52 to 53 of the course textbook. We won't be concerned with trying to remember all of these properties, but they're basically all the properties that you'd expect to hold and all the properties that are desirable for us. So one thing that you may not have noticed, but which is important to observe, is that the study of vector spaces and linear algebra, i.e. everything you saw in Math 200, can be developed in a completely algebraic way, which is perhaps not too surprising considering it's a course in algebra. What I mean is that you don't need any geometry to develop linear algebra. Of course, you may have seen some geometric interpretations of linear algebraic objects, but this would have been there to help you try and gain some intuition about linear algebra methods. But really, you could take a course in linear algebra and never see any geometry and never have to draw anything to help you understand any of the theorems or main ideas from linear algebra. Now, here's a great quote by Sir Michael Atiyah, Fields medalist and my mathematical grandfather, and I'll let you have a little read of this on your own. So the dot product is an object that allows us to take geometry and put it back into linear algebra. So remember, I just said that linear algebra can be developed in a purely algebraic way. Well, if we want to get some geometry back into linear algebra, the dot product is the thing, it's the gadget that we use to come back up with geometry. Really, the dot product gives us back Euclidean geometry. So you may remember that the dot product has this funky definition. If I take any two column vectors, x and y, then their dot product is formed by multiplying each of the components of x and y together and then adding all of these products. Notice that this produces a number, a scalar. And again, the dot product satisfies a bunch of properties that you can find on page 19 of the course textbook. So it's important to remember that the dot product is an operation which takes in two vectors, and these two vectors have to be of the same size, they have to live in the same vector space, and the output a scalar. This is quite different from what you've normally seen when you take products of numbers, say, is because when you take a product of numbers, is you take two numbers, multiply them together, and you get back another number. But here we're taking two objects, two column vectors, which have the same type. We're taking a product of these two objects of the same type, but now we're producing a scalar. And a scalar is an object of a completely different type than a column vector. Also observe that with this definition of the dot product, it doesn't seem too obvious that we've been granted our geometry back and, in light of Atiya's comment, our souls. So let's see how we can get back some of our geometric intuition. Well, one of the first observations is that if I take the dot product of any column vector with itself, then this produces this quantity here. Now this looks very familiar and looks very similar to expressions we have appearing in Pythagoras' theorem. And indeed, it is this fact that allows us and leads us to the following definitions. Given any column vector, we will define its length or magnitude to be the square root of the quantity formed by taking the dot product of x with itself. It's useful to write down what this means when x is a column vector having two entries in it, so it's a 2 by 1 column vector, or a vector inside R2, and you'll see that this is in fact going to be precisely the length of that column vector if you drew that column vector inside the plane. We can also define the angle theta between two column vectors x and y using the following formula. What we mean by this formula is that theta is the inverse cosine of the dot product of x and y divided by the magnitude of x times the magnitude of y. And in fact, this is a consequence of a theorem that you may or may not have seen called the Cauchy-Schwarz inequality. And this is actually why the Cauchy-Schwarz inequality is really important, even though it's a very difficult inequality to try and remember. So let's get back to some geometry. So you will have remembered, or you may remember from high school, seeing geometric vectors. What do I mean by a geometric vector? I mean just an arrow. So normally, at least for me, when I first learned about vectors in physics, I had it drilled into my head that a vector was an object that had both magnitude and direction. Moreover, we can in fact add these geometric vectors or these arrows. If I take two arrows, A and B, I can form their sum, A plus B, by sliding B along A so that the tail of B is at the tip of A. Then the product is the arrow that I would obtain, the sum, sorry, is the arrow I would obtain by starting at A and drawing the arrow to the end point of B. Moreover, in R2 and R3, we can visualize column vectors as arrows starting at the origin. So here, I and j are going to be perpendicular unit vectors. So given a column vector x, say the column vector 2, 1, I can visualize that column vector as the arrow I would obtain by moving 2 units in the I direction and 1 unit in the j direction. Or I could also write this as 2I plus j. More generally, given any 2 points, P and Q, we can draw an arrow from P to Q, or from Q to P, as follows. We would call this arrow, the arrow from P to Q, the displacement vector from P to Q. Okay, so now we're going to have a bit more of a confusing setup, but just bear with me for 1 second. So let's suppose that we start off with 2 points P and Q. Here's P and here's Q. And suppose that as points in the plane, or they could have also been points in space, but I'm just going to consider them in the plane for now. Let's suppose that their coordinates are x1, x2, and y1, y2. Well, of course, given this list of numbers, I could form a column vector x and a column vector y. Let's think about how the column vectors are related to these displacement vectors. Well, we could think of the displacement vector from the origin to P. The displacement vector OP is the same as moving x1 units in the I direction and then x2 units in the j direction. Similarly, we could think of the displacement vector for Q as corresponding to moving y1 units in the I direction and y2 units in the j direction. So based on our geometric description of adding arrows, we would see that OP plus the displacement vector PQ equals the displacement vector OQ. This is this formula we've got underneath the diagram. Well, OP we can identify with the column vector X, and OQ we can identify with the column vector Y. Now we will call OP and OQ position vectors of X and position vectors of Y. So we'd see that the displacement vector from P to Q will correspond to the column vector which sits in the middle of this equation. So that means that the displacement vector PQ has to correspond by vector arithmetic to the column vector y minus x. So now we're going to see how we can use displacement vectors to provide a description of a certain curve in the plane. This curve is going to be called the cycloid. So let's imagine that you've marked a point on your unicycle wheel, purple dot. Let's suppose your wheel has radius r, and ride it at uniform speed in a straight line from left to right. The curve that you would get as you traced out where the purple dot on your wheel was in front of you is called a cycloid. So here you want to think of each of these circles as corresponding to the position of the unicycle wheel after a certain amount of time, and the trace that's been traced out, i.e. this purple curve, is the position of the purple dot as you're moving from left to right. So using displacement vectors, we're going to provide a parametric description of the cycloid, of this purple curve. Okay, so what we really care about is trying to understand where the purple dot on the wheel is going to be after a certain moment in time. Well, to determine where P is going to be, that's the same as trying to figure out the position vector OP, by our geometric vector addition, this would be the same as determining where the center of the unicycle wheel is. Let's call the center of the unicycle wheel A, and also determining the displacement vector from A to P. Well, let's start with where the center of the unicycle wheel will be. So notice as we're moving along from left to right in the I direction, the center is always going to be at the same height because we have a wheel, and this wheel is a circle and it has a radius r. So this means that the point A is always going to be r units in the j direction. Or what's also the same thing is saying that its second component is always going to be r. So now we'd like to ask, well, how many units in the I direction have we moved? Or has the center moved? Center of our unicycle wheel. Well, this is the same as figuring out the length of this arc from the point B to the point P. If we consider T to be the angle subtended by the straight line AP with the vertical line going straight through A, which is the line A to B, then a basic fact from high school geometry is that the length of any arc of a circle of radius T, and let's suppose that that arc corresponds to T radians, this length is in fact T times R, where R is the radius of our wheel. So now we just need to figure out, well, how can we determine the displacement vector A to P? Because once we figure out this displacement vector, we've just determined this displacement vector, and this will give us the position of the point P. Well, the nice thing about displacement vectors is that they don't really care about a fixed origin. They only care about direction. What I mean by this is that arrows can be moved around in the plane and they don't really care where their starting point is. Of course, if we want to add two arrows together, then we have to make sure they're starting at the same point. But I could move arrows around and they don't care about having a fixed origin. So this means, based on this observation, that in fact we can forget about everything outside of the wheel, and we can actually shift the origin to now being at the center of the wheel, to being at the point A. So again, we have our fundamental directions, I and J. We've shifted them, so now they're starting at a new point, but as arrows, we've just said that they don't care about where they start from. And this allows us now to figure out this displacement vector, AP. So notice that to figure out the point P with now respect to this new coordinate system, we'd see that using basic trigonometry, the point P is going to be sitting r times cosine of 3 pi over 2 minus t units in the I direction. And similarly, P is going to be sitting in r sine of 3 pi over 2 minus t units in the j direction. Some basic double angle formula from trigonometry tells us that we can actually collapse and simplify these cosine and sine terms until we end up with the displacement vector from AP is in fact minus r sine t times I, the fundamental direction vector, minus r cosine t times j. So putting this all together, we see that if we let x of t be the position of the purple point on the wheel after the wheel is rolled through a central angle of t radians, then the point P is going to be at the position given by this formula. This is what we call a parametric description of this curve, and we will see this next week.